Good morning, everyone. My name is Dan Fullerton, and today we're going to go over the 2018 AP Physics 2 free response questions. There are 4 of them, and they have not yet released the scoring guide for these, so this is my best quick first attempt. Odds are I probably made a couple mistakes as we go through here, but hopefully minor. But getting this out quickly, I'm hoping at least you get an idea how you might have done on the exam or how to go about attacking these sorts of problems. So with that, let's dive in. Question 1 looks like our electromagnetism question. We've got a couple conducting loops at 3 instants in time, and they're moving at a constant speed into this region of a uniform magnetic field. In a coherent paragraph-length response, compare the magnitude and direction of the current at times t1, t2, t3, and explain why there is or isn't a current in the direction. Well, I'm not going to write the whole paragraph while you guys are watching, but I'll show you how I would go about figuring out what's going on and then let you construct the paragraph from there. So first, it looks like at the t1 time, that diagram on the left, we are going to have an induced EMF equal to the opposite of the time rate of change of the magnetic flux. Or if we wanted to calculate its magnitude, that's just going to be BLV, where L is the width of that conducting loop as it goes in there. Now, we can use Lenz's law to figure out the direction of the induced current. It looks like as that loop moves into the magnetic field, we are increasing the flux, pushing into the plane of the page. That means that the induced current is going to create a magnetic field that would oppose that. So it's going to create a magnetic field that would come out of the plane of the page toward us, which would be counterclockwise by Lenz's law. And this isn't asking about EMF, it's asking about current. So current is just going to be your EMF divided by that resistance of the loop, which would be BLV over R. So there's our starting point. Time 2 looks like we're in pretty much the same circumstance. Our loop is a little bit further into the magnetic field, but the rate of change of the magnetic flux through the loop is the same. So T2, we're going to have the same current, direction, EMF, all of that as T1. Now when I go over here to T3, while it is completely in the magnetic field, even as that loop moves through the magnetic field, the flux through that loop isn't changing. So if there's no change in flux, the induced EMF is going to be 0, therefore the current's going to be 0, and we don't have to specify a direction. So I think that would get you through part 1, part 1A pretty well. Now for part 2, the loop is removed. A proton traveling to the right in the plane of the page is shown, enters a region of magnetic field with the speed of 3 times 10 to the 5th meters per second, gives us the magnitude of the field, and says find the magnitude of the force on the proton as it enters the field. Well, the magnetic force on a moving charge is Q times V cross B, or the magnitude of it is going to be QVB sine theta, where our charge, the charge on our proton, is 1.6 times 10 to the minus 19 coulombs. Our speed it gives us is 3 times 10 to the 5th meters per second. Magnetic field strength, 0.03 Tesla. And sine theta, well, the velocity vector and the magnetic field vector are perpendicular to each other, so that's going to be sine 90 degrees. Sine 90 is 1, so that just all works out to be about 1.44 times 10 to the minus 15 newtons by my reckoning. All right, so that covers us for B1. Taking a look here at B2, it now says, sketch a possible path of the proton as it travels through the magnetic field and label the path P1. Well, the nice thing here is a moving charge going through a magnetic field. The magnetic field can't do any work on the charge. It can only change its direction because the force is always perpendicular to its velocity. So looking at the right-hand rule, if I point the fingers of my right hand in the direction our positive charge is moving, here to the right, and I bend my fingers in the direction of the magnetic field into the plane of the page, I'm going to see a force that is upward. The direction my thumb points would be up. So it's going to feel a force upward when it first gets in here. And as it keeps moving around, as that direction changes, as it accelerates, that magnetic force will always be toward the center of the circle. So I expect what we're going to see is a circular path, something kind of like that. And let's label that P1. Now for part B3, we're going to put a second proton into the magnetic field at the same point and from the same direction, but at a greater speed than the first. And we're supposed to draw its path. Well, obviously that's going to be a circular path, but with the higher speed, what happens to the radius of our circle? The way I would go about attacking that is taking a look at that magnetic field, which is equal to QVB sine theta, just its magnitude we're worrying about, is also a centripetal force. So that's mv squared over r. It's causing something to move in a circle. So from this, we can then solve for r. Looks like we'll have a velocity, cancel out. Sine theta is going to be 1. So r is going to be mv over qb. M is a constant, Q is a constant, B is a constant, V is not. So as V increases, I'd expect our radius to increase. So our second proton, coming in here with the higher speed, is going to make a circle with a greater radius. So that one's how I would draw our P2. And part 4. Next, an electric field is applied in the same region as the magnetic field, so there's no net force on the first proton. Okay, so as this enters the magnetic field, the first proton entered the magnetic field, we had a magnetic force upward. We're going to need an electric force, and therefore an electric field pointing down, because the electric field is in the same direction as the force on a positive charge. So calculate the magnitude and indicate the direction of the electric field. For part B4, we could say that the direction is going to be down, and the magnitude of it, well, for it to go straight through, the net force has to be 0, no acceleration. Therefore, the upward force of the magnetic field has to match the downward force of the electric, from the electric field. Therefore, we could state that QVB sine theta, the magnetic force, must equal QE, the electric force. All we have to do then is solve for E. Again, Q's cancel out. Sine theta is going to be 1. E is going to be equal to VB, or 3 times 10 to the 5th meters per second, times our magnetic field strength, 0.03 Tesla, which works out to be about 9,000 newtons per coulomb. Whoops. Went a little bit to the left there. So I think that covers us for number 1. All right, let's take a look here at number 2. Looks like our circuits question. We've got a circuit with 2 resistors and a switch initially. Complete the diagram to show how the ammeter and the battery should be connected to experimentally determine the resistance of each resistor. Describe the experiment by listing the measurements to be taken and explaining how the measurements would be used to calculate resistances R1 and R2. All right, so first thing here, what I'm going to do is draw our circuit. Looks like we've got R1. Up here we've got R2. Down here we've got a switch. These come back together, and over here to point B. Well, not a whole lot of places we can do this, so seems pretty obvious to me. Let's put an ammeter in line with our 9-volt battery. And that can be our circuit. All right, so describe the experiment that would allow us to calculate R1 and R2. Well, first thing I'm going to do is I'm going to close the switch. When I do that, when I close the switch, as current flows, it's going to go through R1. It's going to completely bypass R2. It sees a path here with no resistance compared to some resistance. All the current will go through the switch, through the ammeter, and the battery. So really what we end up with is effectively a circuit that has a battery, 1 resistor, and an ammeter. So when we do that, all 9 volts is dropped across R1. So in that case, R1 equals V over I by Ohm's law, which will be our battery voltage over our ammeter reading. So we can come back to calculate what that is in a little bit, but R1 should be pretty easy to calculate. All we need to know is what the ammeter says and what our battery is. It tells us below that's going to be 9 volts. Now, we can also then go open the switch. When we open the switch, what we effectively have is a series circuit where the current goes through R1, then R2, through the ammeter and back to the battery. It's as if this branch doesn't exist. So now, all 9 volts dropped across R1 in series with R2. So our current flow now, our ammeter reading, I equals V over R, is going to be our battery voltage, 9 volts over R1 plus R2. Or, rearranging for R2, that'll be 9 volts minus the voltage drop across R1, which will be IR1 by Ohm's law, all divided by the total current reading. So that's what I would do as far as explaining how you would build the circuit and what you would do in order to determine R1 and R2. Now it says a second group of students is given a combination of circuit elements similar to the previous one, but has an uncharged capacitor. The combination is placed in a circuit with a power supply, so the potential difference between A and B is maintained at 9 volts. The students close the switch, immediately begin to record the current through point B. The initial current is 0.9 amps, and after a long time, it's 0.3 amps. So let's go on to the next page here, and we'll start working on 2B. Our circuit now looks like this. There's our point A again. We have resistor R1, a split over here to R2. Still have our switch, but now we also have a capacitor to go along with it. And over here to point B. All right. So for 2, it says compare the currents through resistor 1, resistor 2, and the switch immediately after the switch is closed to the currents a long time after the switch is closed, and states if any current is 0. Well, initially, the capacitor is going to act like a wire. So let's draw an equivalent circuit right at time t equals 0, right after that switch is closed. So an equivalent circuit at t equals 0 would look like this. R1, right there. The capacitor acts like a wire, so we're going to just have a short when this is closed through here. We're going to completely ignore R2. All the current will go through this path immediately after that switch is closed. So really what we have here is our ammeter and our battery. Nice simple circuit there. So just like we talked about previously, in this case, the current through R1 is going to be equal to our battery divided by R1. It tells us our battery is 9 volts. Let me rearrange that first. IR1 equals V over R1. What we're looking for here is R1, so therefore we could say that R1 equals V over IR1, which is going to be 9 volts over the current through R1 is 0.9 amps, which is 10 ohms. Just be careful. I said that quickly. IR1 isn't I times R1. What I'm writing here is the current through R1. So that's the current reading through your ammeter. IR1, I can make that a little clearer here too. I subscript R1, if that's a little easier to see. Just using Ohm's law, R equals V over I. Therefore, R1 equals 10 ohms. Okay. Now, in this case, there's no current flowing through R2, so we've got R1 equals 10 ohms. It's asking us to compare the currents, so we know that the current through R1 here is 0.9 amps. The current through R2 here is 0, nothing's flowing through it, and the current through the switch is going to be all of the current. It's completely bypassing R2, so that will also be 0.9 amps. So we've got these different things to help answer our comparison question. Now then, it asks us to go and take a look at the equivalent circuit now, or what happens as t approaches infinity, or after that switch has been closed a long, long, long time. Well, after that's been closed a long time, that capacitor is going to act like an open as it's charged up. So our equivalent circuit now is going to look like we have R1 in series with R2. We've still got our ammeter and our power supply, our battery, 9 volts. So in this case, the current through R1 and R2 has to be the same. I equals V over R, which is going to be our battery over R1 plus R2. Add those resistors in series. Therefore, R1 plus R2 equals V over I, which is going to be 9 volts over, it tells us the current here is 0.3 amps or 30 ohms. But since we already know up here R1 equals 10 ohms, this implies then that R2 must be equal to 20 ohms. And in this configuration, our current through R1 is equal to the current through R2, which is equal to 0.3 amps. Nothing's going through the switch here, so current through the switch in this case is 0. So you could use that data in order to determine and answer the detailed questions it's asking about what's going on in these different configurations. All right, now it tells us a third group of students now uses the combination of circuit elements with the capacitor. They connect it to a 9-volt battery that they treat as ideal, but which is actually not ideal and has internal resistance. So now they're going to build the circuit. They're not going to realize this battery has some extra resistance to it. It's a non-ideal battery. It's a real battery. What we want to know is how does their value of R1 compare to the second group's value? Well, I would say that group 3 is going to calculate a larger R1. Some of the 9-volt battery's potential is dropped across the resistance of the battery, so less than 9 volts is dropped across R1. If group 3 assumes that all 9 volts is dropped across R1, then they're going to calculate a smaller current, so they're going to get a larger value for R1 since R equals V over I. Use a smaller current, V over I, you're going to get a larger resistance. So something to that effect in a couple sentences I think would probably cover you for 2B and for 2C. Question 3 says we have monochromatic light of frequency F shining on a metal as shown above. This has sounded like the photoelectric effect. The frequency of the light is varied, and for some frequencies, electrons are emitted from the metal. The maximum kinetic energy, K sub E, of the emitted electrons is measured as a function of the frequency of the light. So for A1, based on conservation of energy, the relationship between KE and frequency is predicted to be AF equals B plus KE, where frequency is greater than F0 and kinetic energy equals 0 when the frequency is less than or equal to F0 and A and B are positive constants. And it shows us a graph. We want to talk about which aspects of the graph correspond to A and B and the physical meaning of A, B, and F naught. That's a lot of questions, but really what it's asking, I think, is do you understand graphs of the photoelectric effect? So taking a look to begin with at that formula, they have AF equals B plus the kinetic energy. That's not the usual way I see that written, though. Typically, we would write this as the kinetic energy is equal to that constant A times F minus B. And there's your y-axis, so on the graph, y equals, A is going to be your slope, m, F is your x-axis, plus B, your y-intercept. So the y-intercept is going to be the opposite of negative B. So the first things I would note here, A is your slope. So let's come over here to the graph and note that our slope here equals A, and the slope of that I know is Planck's constant. So A is Planck's constant, and we pointed out what that is on the graph. This F0, F0, is what we call the cutoff frequency. That's the point at which you do or do not get electrons. Higher frequencies than F0, then the incoming photons have enough energy to free an electron. If they have a lower frequency than that, the incoming photons don't have enough energy to free an electron, and any leftover energy becomes the kinetic energy, which you see there. And if we were to trace this back, the y-intercept where it crosses there, that is the opposite of B, which is going to be, let me write that in a color that's a little easier to see. That didn't help, did it? Let's try that again. That point, that y-intercept where it crosses, y-intercept is opposite of B, which is what we call the work function, the amount of energy that's required in order to free an electron. So, I think that covers us for A. A2 says, explain the physical meaning of the horizontal section of the graph between the origin and F0. So it's talking about what's going on there. And for that, I would explain something to the effect of, in that region you don't have any emitted photoelectrons because the incoming photons don't have enough energy to free an electron. Or you could look at that as the energy of the incoming photon is less than the work function of the metal in that region. So that covers us pretty well for A2. A3 says we get a second metal with different properties than the first metal. On the figure below, the dashed lines are the same lines as above. Okay, that looks similar. But we're supposed to sketch lines on the graph, on the figure, that could represent the data for the second metal. All right, let me do that in red so it's easy to see, but let's do a second metal like this. The slope of this has to be the same because the slope is always Planck's constant regardless of the metal, but we could have a different F0, a different cutoff frequency. So you probably want to point that out. Different cutoff frequency. You could also trace that back and show a different work function, a different y-intercept, but it only says to explain one, and it's a time test, so let's not dig ourselves any deeper than we have to. All right, moving on. We're going to take that same concept now and apply it to an electroscope. Talk about seeing an electroscope that has leaves slightly separated because it has a negative charge, and ultraviolet light shines on the sphere, causing the leaves of the electroscope to move closer together. So our basic electroscope, there's our leaves. We have the bottom of this insulated in some sort of box or glass, things like that. And we're going to shine some light on it. The leaves come closer together as we shine the light on it. We know it's negative. What's going on? Well, what I would say is these photons, as they hit the metal, the incoming photons must have an energy greater than the work function of the metal. They have a frequency higher than the cutoff frequency. So as they hit the metal, they are freeing electrons, and some of that negative charge that's residing on the metal is going away. This is becoming less negative, therefore the leaves go closer together. As there's less charge, there's less coulombic force pushing the leaves apart. Green light then shines on an identical negatively charged electroscope and nothing happens. Well, if instead of whatever frequency, color, energy of photon we have here, if we go to green and it's not doing anything, that means those green photons don't have enough energy to free an electron. The energy of those incoming photons is less than the work function of the metal, where the cutoff frequency of the metal is greater than the frequency of the incoming photons. The photons need to have a high enough frequency to free the electrons, and green light just doesn't do it. C says the brightness is increased. Brightness is just the number of photons, so we send more of those green photons at it, and what happens? Well, nothing. You can send as many as you want, make it as bright as you want. Doesn't change anything until you adjust the frequency to the point where you have a high enough frequency that it's greater than the cutoff frequency and you free electrons. So more electrons with not enough energy doesn't help you at all. You need higher energy or higher frequency electrons in order to, or higher frequency photons in order to free the electrons. So I really like this as a question really testing, do you understand the photoelectric effect? Number 4 is a question that's kind of all over. We're going to start with a boat. Has a mass mb, can displace a maximum volume vb. It's floating in a river with water density rho, with steel beams that have density and volume, and they want to carry as many beams as possible. Find an expression for the number n of steel beams you can have before the thing sinks. All right. Well, this to me looks like we're looking at the buoyant force. So I'm going to start with the free body diagram. We know the buoyant force has to balance the weight of the boat, which is going to be mb, the mass of the boat, times the acceleration due to gravity here on the surface of the Earth. And we also have the force, the weight of the steel, which is going to be the density of the steel times the volume of the steel times g. So if those are all in equilibrium, not accelerating, we've got them just balanced to the point where we have as many beams as possible on there, our buoyant force is the density of the water times the volume of our boat times g, and that has to be equal to our weight of our boat, mass of the boat times the acceleration due to gravity, plus our number of steel beams times the weight of each steel beam, rho steel, times the volume of the steel times g. Looks like quite a long equation, but really all we have to do is take this portion of it here and solve for n. A little bit of algebraic rearrangement leads to n equals the density of the water times the volume of the boat minus the mass of the boat, all divided by density of steel, volume of steel. So a pretty intimidating question at first glance, but really not bad when you dive into it. Okay, now it says the captain realizes oil's leaking from the boat, creating a thin film of oil on the water surface. In one area of the oil film, the surface looks mostly green. Explain in detail how constructive interference contributes to the green appearance. Assume the index of refraction of oil is greater than the index of refraction of water. Wow, so we have really switched gears. This really has nothing to do with the boat anymore. Now we're doing a thin film interference problem. So question 4 is kind of like, 4b is almost like a whole new question, but they're short little questions. So for B, let's give ourselves a little more room here. What we have is we have an interface where we have air, we've got some thin film of oil, and we've got water, and we know the oil has a higher index of refraction than the water underneath. Well, what's happening is we have light that's coming down, and when it hits this interface, part of it is reflected, and part of it is transmitted into the oil. And when it hits the oil-water interface, again we have reflection. So that beam now travels a different distance before it comes back and sees this one. And if it's traveling a different optical path length, different portions of that ray are meeting with the different portions of the initial ray. So you can have interference. The beam can interfere with itself. Now, what goes on in a little bit more detail as we're looking at that is as that light hits the air-oil interface, some's reflected, some's transmitted. The part into the oil partially reflects at the oil-water interface, but it also undergoes a phase change as it's reflected, resulting in an additional optical path difference compared to that initially reflected ray. The reflected ray from the air-oil interface, right here, and the ray from the oil-water interface constructively interfere due to that shifted optical path length difference of the ray traveling a longer distance coupled with that phase shift. And based on the thickness of the oil, this occurs most strongly in the case of green light, which has a wavelength of around 550 nanometers. Which means that oil film has a thickness of roughly 1/4 the wavelength of the green light in the oil. So I'd probably walk through some sort of explanation like that. The whole thing, the whole question is worth, what's it say there, 10 points. So I don't know how much detail I would really go into there, especially around phase changes and calculating what a potential thickness of the oil film is. You might be fine just with showing the two different optical path lengths of the beam, and might be wise to point in the phase change due to the difference in the indices of refraction, the oil being greater than that of the water there. So that should cover you pretty well for part 4B, I would think. Basic explanation of thin film interference. And C looks again like a completely different question to me. For C, we have the boat floating down the river with the water current heading for a town, and it looks like this really has nothing to do with the boat. The river has a width of 60 meters, so 60 meters across, the width of our river here, and a constant depth, and flows at a speed of 5 kilometers per hour. That's our V1 as it floats downstream. Partway to the town, it narrows to 30 meters across. Same depth, but new speed. We need to figure out what that new speed is. So this, to me, looks like the fluids topic with the continuity equation, where the area over here, whatever that happens to be, area 1 times the velocity at 1 must equal area 2 times velocity 2, where this is area 2. The nice thing here is because it's constant depth, our area, I'm going to model as a rectangle, length times width. If it's got constant depth, constant L or W, the other one's the same. So we could write this as 60 meters times whatever our depth is times V1 must equal 30 meters times whatever our depth is times V2. Don't care what the depth is, it cancels out. What we end up with is 2 V1 equals V2. Or V2 equals 2V1, which is 2 times 5 kilometers per hour, or 10 kilometers per hour in that skinnier section of the river. And with that, I believe we've covered the entire AP Physics 2 free response exam. Hope that gets you a good start, has you feeling pretty good about what you might have done, or makes you feel better as you're preparing for future year exams. Thanks so much for your time, everyone, and make it a great day.